Yeah, some of them I set up to automatically record and some I haven't. All right, so thanks for the reminder. Okay, so let me share again. That's helpful. All right, and I'm going to put my little thingy over here. So hopefully that'll be in the picture. Okay, so there are two types of delays. There are inertial delays and transport delays. Inertial delays are synonymous with propagation delay. So inertial delay is like the official name, but at least in Verilog it is. But a lot of people talk about propagation delay. I talked about until I started writing Verilog code, I never even heard the term inertial delay. So the more common term is propagation delay. But in Verilog, we differentiate between inertial delays. Now, back to what I was saying earlier. All this is strictly for simulation purposes. It has nothing to do with what actually works out in the hardware, because you can write whatever number you want there, but just keep in mind that doesn't change the rules of quantum mechanics, right? Quantum mechanics goes on whether you write 5 there or 5,000. Quantum mechanics is what it is. So when you build a transistor switch or a transistor gate, the size of the features, the type of design of the gate, the current, the voltage you run it at, the parasitic resistances, capacitances, inductances, those all determine how fast those gates actually work. And so it's all dependent on the target hardware, the foundry you're using, the material you're using, on and on and on and on. The field programmable gate array, FPGA that you're using. And in the case of Xilinx, you can buy a part and then program it and run it. And if you're just a little, if your timing is just a hair off, you can probably go back and spend more money and buy a part from Xilinx that's exactly the same, but has a slightly higher speed rating. And in that case, you might actually get it to work, whereas the lower speed rated, but otherwise identical part didn't work. And that's because when they manufacture these things, then they measure the speed on them, and some of them actually run a little faster than others, or at least some batches may be better than others. And it's because, the steps in the foundry are not, they're pretty accurately controlled, but they're not perfect. And that brings up another interesting phenomena in the world of integrated circuits that's really, really interesting. And I'm just going to throw this in here, but it is really important. It's something you should be aware of. We're able to work on tolerances in manufacturing integrated circuits that no other field I can think of can even come close to. I think in integrated circuits, you can certainly work with maybe a 5% tolerance on feature sizes and when you actually fabricate the chip, how things actually go. Imagine if you were building a house and your boss said you can work with 5% tolerance. And so you were supposed to cut a board 100 feet long, but you cut it 95 feet long because you had a 5% tolerance. I guarantee you those 5 feet would be significant, cause real problems, right? And but in integrated circuits, you can live with those kinds of tolerances for the most part. There may be exceptions, but in general, we can work with those kinds of tolerances. And that's partly due to the fact that it's digital and everything gets pushed into ones and zeros. And so there's a fair amount of room for slop. That's one of the reasons that integrated circuits are so reliable, because they can operate with pretty large tolerances and still work perfectly. Whereas in most other areas, you can't even begin to tolerate something like a 5% tolerance. So that's a really interesting point. Okay, so inertial delay. We also talk about transport delay. You can think of the transport delay as the time it takes for the speed of light to go the very small distances inside a chip. And that's compounded by the fact that the transistor switches in these big interconnect matrices that allow you to program these big chips. So the thing that makes these chips programmable is you can change how signals are routed through the chip by clearing and setting bits that control transistor switches in these big interconnect matrices. And these switches are not instantaneous. So when the pulse runs through one of these switches, there's a little delay associated with that. And as a result, there is significant, at least at the nanosecond scale, potential for transport delay. And especially if it's routed poorly, and maybe it goes in and out of the transistor switch a couple of times and runs all over the chip. You know, on a good size integrated circuit, it's maybe an inch in size. You could run around several times and maybe log a bunch of inches. And when you think that 1 nanosecond's a foot, and you throw in the delays through the switches in the big interconnect matrix, you can certainly have a fair amount of transport delay. So we specify these two different types because when we simulate our circuit, the inertial delays are treated by the simulator differently than the transport delays. And the difference is that if you have a pulse shorter than the inertial delay, it won't propagate through the gate. Whereas if you have a pulse shorter than the transport delay, it is propagated. And here's the timing diagram to show that. Here is X, which is the input to whatever circuit we're talking about here. In this case, we're just setting it equal to Z with a transport delay of 10 nanoseconds and an inertial delay of 10. So X goes up to 1 and it stays up for 10 nanoseconds. And 10 nanoseconds later, Z becomes 1 and stays up for 10 nanoseconds and then goes back down. And the same for Z2, which is the propagation delay. But in the case of the second pulse, we have a little 2 nanosecond pulse in the middle that is not propagated in Z2, the inertial delay, but it is propagated in the transport delay because the transport delay doesn't filter anything out. And that's because you can think of this more as a wire. Yes, there's a delay of the speed of light down the length of the wire and through some of the transistor switches adds a little bit, but a short pulse is still propagated because it's really just a wire. Whereas in the inertial delay, the short pulse is not transmitted because the gate actually has a certain amount of time to finally get up so it can change its output. And if the stimulus, in this case, this little negative down pulse to 0 of 2 nanoseconds, if it goes away too quickly, then that process will never finish and the output will remain what it was. Now, you might actually see it start to change a little bit here and then go back down or something. There might be a little bump. But because everything's quantized to zeros or ones, that will never read as a 1. It'll always read as a 0. Okay, so we have a number of steps when we design a circuit using Verilog. And if you've already now worked with Vivado, so you know that there's a whole list of steps over there, including elaborating the design, and then a pre-synthesis simulation, and you can do a post-synthesis simulation. So basically, you put in your source code, and then it gets essentially analyzed, and then you get this intermediate code, and then it gets this working library, and then there may be some other libraries you've added IP from, and then it elaborates a design, and then that generates this net list or simulation data that goes into the simulator, and then you can simulate. And this first simulation step is pre-synthesis. Then you synthesize things, and then that's when you generate the official net list, and then you do a post-synthesis simulation, and then you do placement, mapping, and routing, and then you generate the bit file, and you're done. But there are a whole bunch of steps, and you want to simulate it before synthesis, you want to simulate it after synthesis, and it turns out something may look like it's going to work before you synthesize it. After synthesis, there may be problems. And particularly for integrated circuits, we want to validate and sign off on every step, so that when we actually go to the foundry, we're going to have a successful chip, and we're not going to have problems in it as much as is humanly possible, because it's very expensive to make bad chips. All right. And this, you're now in Vivado, it checks your syntax as you type it in, which is actually really nice. And then it will also check your library references and all that. So the Verilog code then gets converted to this intermediate form, which actually then can go into the simulator. Now, how does the simulator actually work? Well, it uses this, what's called discrete event simulation. And so the simulation always works in simulation time. And so it's a completely artificial construct, right? And so it operates in discrete steps of simulator time. It has it may be that you've set the granularity of simulation time, say, to be a nanosecond. So what it does, it operates in discrete steps, and then it has we'll see this initially, or we'll see this in a minute, where it has what's called even within the same nanosecond, it still orders events. So it creates these events, and each one is spaced sometimes by what's called the delta time, which is an infinitesimal amount of simulator time. And then eventually that delta time jumps to the next nanosecond, or next 10 nanoseconds, or whatever the next event actually happens. But at some point, there may be several events all within the same moment that are separated by this delta time. We'll look at this in a second. And so Verilog statements are executed and corresponding actions are scheduled. If you've specified a delay, either a transport or inertial delay, then those are used to do the scheduling. And that's called a scheduled transaction. But if say the stimulus goes, the change in the signal goes away before the scheduled time occurs, in the case of inertial delays, then that event is descheduled and it never occurs. All right, so simulation process. The initialization phase assigns all the initial values, and then you do the actual simulation. And we always remember, when you're simulating, your test bench code is generating all the signals, including the clock and all the external signals that are being fed in to your module under test. We call it the device under test, DUT. So the device under test, your test bench is providing all the signals in, and then it's getting the signals out. And what it does with them is up to you, but you can write code that allows it to compare the values out with the expected values, or you can just plot the values you get out in a timing diagram in the simulator, and then you can inspect it visually to see if it's correct. All right. Because in simulation, we always have to specify all the initial values, we use a lot of initial blocks, or we use initial blocks in the simulators in the test bench code. And you can specify it. Now, it turns out when you're programming an FPGA, you can also use initial blocks in your row code, in your actual modules. But you can't use those when you're making a chip from scratch, because when the chip powers up, you have no idea what the initial states will be unless you've built in special initialization circuitry. But in the FPGA, you get a program in the initial state, so you can specify. You can, to some degree, you can specify that. So if you don't if you don't initialize values, then the simulator will just assign a default value. And what it does, it depends on whether it's a wire or a register. If it's a wire, it's gonna show that it's disconnected, and if it's a register, it'll show that it's unknown. But in Verilog, those two things are the same. They're actually different in VHDL. Then it sets the simulation time to time 0, and then each process block, which would be your always blocks and initial blocks, are activated. The initial blocks are obviously started because they run at 0 time, and if the always block is triggered, then it would run also. Otherwise, it waits until, say, the clock would be the right edge, for instance. So the scheduled transactions don't happen until one reaches the scheduled time. All right. So here's here's some code. So we have here, so what are these? Are these inertial delays or transport delays in these two assignment statements?
Initial.
That's right, they're inertial delays, because transport delays would be on the other side of the assignment operator, the equal sign. All right, and here we specified no delays. So if a statement has 0 delay, it still gets this infinitesimal delta delay, but it doesn't advance the actual simulation time. So if you're stuck at, say, at 1 nanosecond, a delta delay added to 1 nanosecond, still 1 nanosecond. But it's used to schedule things because they do have to be scheduled in some order, and there's generally an order that's, well, it has to have some order, and so they use this order spaced out by delta delays within a particular simulation moment. Okay, all right. So here's an example of delta delays. We have 3 inverters. We put in B is going to be changed to B prime. B is going to be equal to A prime after the first delay. C is going to be equal to B prime, which would be A prime after the next, or C is going to be equal to A. And then D is going to be equal to A prime again. So you can write this: B equals A prime, or the inverse of A, C equals the inverse of B, and D equals the inverse of C. But this last one, we put in a inertial delay of 5 nanoseconds. So here's the way this would be simulated. Now, we're just going to look at this briefly. This is a lot of mental work for very little gain. But if you get to the point where you're exercising your code in the simulator, then you may go back and have to become, if you're working for some company and that's your job and you're doing these simulations, you probably need to understand at fairly high level of granularity or fairly low level of granularity exactly what's going on, including understanding these delta delays and everything. So at 0 nanoseconds, let's say A is 0, B is 1, C is 0, and D is 1. This is what you're initialized to. And then you add 1 delta delay. That adds 1 delta delay. Now, at 3 nanoseconds, so everything except this 5 nanosecond will have run. So at this point, let's say at 3 nanoseconds, A changes to 0. Okay. I'm sorry, it changes from 0 to 1. All right, but B is still 1 because the delta delay is not expired. So now we go 3 plus 1 delta delay. Now B has responded to the change in A, and it's now 0. And then at 2 delta delays, C has responded to the change in B, and it's now 1. But because D has a 5 nanosecond delay, it gets scheduled for 8 nanoseconds. And when 8 nanoseconds arrives, then D changes to 0. So that's how the simulator works. So you can see here, you've got 3 delta delays at the 3 nanosecond time period. So the nanoseconds don't change here. But they are all scheduled at different delta delays because there's no inertial delay for the A gate or for the A buffer, the B buffer, but there is for the C buffer. And that's how that would look in the simulator. All right, I don't care that you spend a lot of time trying to make sense out of this if that was super confusing, but that's how it works. Okay, so we sort of went through that. So these both have delta delays associated with them, because there's nothing specified, and they're infinitesimal amounts of time. They do not change. You're at 3 nanoseconds here plus a delta delay. You're still at 3 nanoseconds plus a delta delay. You're still at 3 nanoseconds. But since the next one has a 5 nanosecond delay, we schedule this 8 out here we schedule this last change of D at 8 nanoseconds. And when we get to 8 nanoseconds, boom, D changes. Plus, this, yeah. Okay. So if you have multiple processes, statements inside each process, the initial blocks and the always blocks, all execute in its own way. If they have blocking statements, then they will be blocking. If they have non-blocking statements, then they'll all be executing simultaneously. If there are multiple process blocks executing simultaneously, then they will be executing concurrently. And all the concurrent statements outside process blocks will also execute at the same time concurrently. Remember, these assignment statements outside always blocks always execute concurrently. And inside process blocks, if they're non-blocking, they execute concurrently when the process block executes. And if they're blocking, then they execute with those blocking considerations. If there's no delay specified, then everything takes delta time, which really renders your simulation kind of useless, frankly. All right, so here's a simulation example. And I'm not gonna go through this. This is very tedious. So if you want to look at these slides and make sense out of it, you're welcome to do that. I have gone through it. I do understand it, and in understanding it, I have decided it's not important for you to sweat over this, because it is kind of confusing. It takes just to figure out their syntax and how they write things. Suffice it to say that we schedule things, but if for some reason they don't happen, things change, then they may not ever happen. And this is really complicated. So notice this always block is triggered by the level signal B, but B doesn't even appear in here. This always block is triggered by the level signal A, and A does appear in the if statement, but it's not part of the assignment. So these have this complex interaction. It's crazy. I don't think it's worth doing. So if you want to look at it and make sense out of it, knock yourself out. But I'm not going to go through it because I think it's largely a waste of time. All right. Now I want to talk about operators, and I'm going to finish a little early so I can get to Micro 1 Lab today. So here we have our Verilog data types and operators. We have what we call nets, which are always wires, and we have registers, which are registers. We also talk about vectors, and those can be wires or registers that are multiple bits. So you can have a wire that's effectively 16 bits, 16 wires essentially. You can have a register that's 16 bits, or 32, or any number actually. But we usually do use powers of 2, but not always. Like in the mid-level PIC chips, the 8-bit PIC chips, the data bus for the program memory is 14 bits wide. Doesn't have to be 16. The address bus is 15 bits wide. So the address bus for the data memory is 12 bits, and then the data bus for the data memory is 8 bits. So they have all sorts of bit widths on the PIC chip operating as buses. But in the KL25Z chip, all the buses are 32 bits. So there are different philosophies of how to lay these things out. Besides a register data type and a wire data type, we also have integer data types. If you're going to do anything besides addition and subtraction, you have to declare it as an integer. And I don't even know, maybe you can't even do subtract. Yeah, I guess you can do subtraction, but with nets and registers, but you can't do multiplication. You cannot do division. And again, these are integers, no fractional portion. If you want to have floating points, then you have to use the real designation. And then there's a special designation if you're storing time information called time. We're probably not going to use time or reals, but we will do some integers. All right, let's look at the operators now. So the first thing about this is it's very, very similar to C. Not identical, but it's very, very similar to C. One of the things that's a little different is down here, the curly braces. The curly braces in Verilog are really only used for concatenation. And that's a little different than in C. In C, we use curly braces for all sorts of stuff, but we don't use them for anything else except concatenation in Verilog. All right, so let's first look at the groupings. So we have logical operators and bitwise operators. And then we have relational operators. Now, relational operators are always, well, yeah, so I was going to make a statement that wasn't quite accurate. So relational operators have to do with, comparing the value. Shift operators, we have a bunch of those. And notice we have this thing with 3 carets. That's an arithmetic operator, arithmetic shift rather. So we have 2 carets as shift. If they're less thans, it's a left shift. If they're right. If they're greater thans, it's a right shift. And if there are 3 of them, it's an aromatic shift left and an aromatic shift right. Now, what's the difference between aromatic and just regular shifts? In regular shifts, you bring in zeros on the when you're bringing the values in. So let me really quickly do this, and then I think I'm probably we'll just finish maybe with this slide. But let me bring up my document camera real quick. And okay. Okay. And all right. Okay, so we have all right. So remember we've used this quite a bit, and so for instance, if we have say we want to put a 1 in the position 17, we'll say for a mask A equals 1 shifted logically shifted left, say 17 times, and then that'll give us 1, 2, 3. Well, let's see. So 31, 32, 31, 30, 29, 28, 27, 26, 25, 24, 23, 22, 21, 20, 19, 18, 17, and then 16, 15, 14, 13, 12, 10, 11, all the way to 0. Okay. So that gives us a 32-bit word with a 1 in the position 17 and zeros everywhere else. If we did, if you did arithmetic shifting, then that, well, I guess it would look about the same with this in this thing. Let's say we have a 8-bit value. So 1, 1, 0, 0, 0, 1, 0, 1. Okay, so an arithmetic shift right will shift all these digits down. So now we'll have 1, 1, 0, 0, 0, 1, 0. This last 1 will just be discarded. What's shifted in at the top? If you're doing a logical shift, it would be a 0. But if you're doing an arithmetic, it replicates that sign bit. Now, if you're shifting the other direction, it gets a little tricky. And generally in C, you're going to shift in a 0. But in Verilog, a lot of times it'll replicate the low order bit. In this case, it would shift in a 1. So that's one of the differences between C and Verilog. Now, you probably have to check and make sure that your implementation does in fact do that, because that can be tricky. So let me get rid of this. Let me go all the way down, and I'm also gonna, let's see, I'm also gonna do this because what I want to check is, so, let's see, well, maybe I better. I'm just going to double check this because now let's see. Yeah, okay. Yeah, that's not, it's not gonna, yeah, here we go. So, yeah, let's, okay, here we go. I think this will explain it. I want to make sure I get this right. And I have, let's see, relational. Ah, man. Well, I'll double check it and let you know for sure. Okay, here, let's do this. No, that's going to be Verilog beginner. Okay, this should be better. Okay. Okay, so logical shift operators simply shift the numbers left or right in vacant positions. And after shifting, all vacant positions are filled with zeros. All right, but arithmetic operators shift number left or right, same as logical, but the most significant byte remains the same for right shift, which we just said. So it basically preserves the sign. So when you shift one, the 0 gets replicated. The 1 gets replicated. If you shift 3 times, you shift in 3 zeros. If you shift 3 times to the right, you shift in 3 ones. But shifting the other direction, you're shifting in zeros. So let's see what they say. For the right shift, yeah. But now what they didn't say. And for left shift, the vacant positions are filled with 0. Okay. So they're claiming that there's no difference. All right, that's fine. So the reason I wanted to look this up is because I have seen it. I've seen it both ways, and so it's always been a little confusing to me. So that particular article claimed that a right arithmetic shift is the same as a right logical shift, and so we'll operate with that on that principle until it's proven differently. Next time you're in lab, you should try it. Define a little variable, shift it, and then display the variable and see what happens. And I will not guarantee you that in the compiler in Vivado will necessarily work that way, but that has been, I've definitely seen both conditions stated. All right. So we'll maybe have to do a little exercise in lab just to check that, see if that's actually true. For sure, in C, it is true. That is how C works. It's implemented that way on microprocessors, and you can generally count on that. All right, notice here we have logical AND, logical OR, logical NOT, and then we have bitwise AND, bitwise OR, and bitwise negation. Now, why they didn't use a double exclamation point and a single exclamation point, I don't know, but they didn't. Notice here we have bitwise exclusive OR, bitwise exclusive NOR, and you can write this either way. You can write caret tilde or tilde caret. But there is no logical exclusive OR, which actually should make sense, right? Because it doesn't, well, doesn't really make sense. Okay, relational operators. We have equality. Remember, if you just put an equal sign in C, you actually set the left-hand side equal to the right-hand side and generate a logical result as well. So you have to use a double equal sign if you just want to compare them. So equal, not equal, greater than, less than, greater than or equal, less than or equal. You have to be really careful in Verilog. You have to make sure that the number of bits is the same and all sorts of things, and it's easy to get this screwed up. And yeah. All right, shift operators. We talked about this already. Now, this is really important. So addition, subtraction, and concatenation. We will use concatenation a lot. So let me just show you how that's supposed to work, because it is a little different. So if we use the concatenation, let's say A is defined as say 4 tick B 0 0 1 0, and B is defined as 4 tick binary 1 1 0 0, and we concatenate those. So if we say C, which is say an 8-bit vector, it equals A plus B, well, then we would get this would be equal to 1 1 1 0. If we say C equals, and there'd be 4, because it's 8 bits, you'd have 4 zeros in that. But if you do this, if you do the concatenation, A comma B, curly brace, then that's going to be equal to 0 0 1 0 1 1 0 0. So it just takes these two and combines them into this 8 bits. And we use this all the time. So for instance, what we might do, let's say we wanted to shift the higher order bit in A and combine it with the top 3 bits in B and set that equal to C. Let's say now C is a 4-bit vector. So then we would write C equals A 2 to, oh, I should have done it the other way. We'll say B 3 equals, we say curly brace B 3 comma A 2 to 0, curly brace. So we're taking the lower 3 bits of A, which would be say these right here, and we're taking the upper bit of B, this one here, and we're combining the B upper bit with the lower 3 bits of A, and so that would give us, in this case, it would give us 1 0 1 0 would be our 4-bit answer. So the concatenation operator allows you to take these vectors and do part select on the vectors, which is what we call it when we don't use the whole vector. We do a part select, and we concatenate a part select of B with a part select of A, and we generate a new 4-bit vector by doing that. This is extremely useful when you want to pull parts of one vector out of another and assign it to a third. So we will use that all the time. Okay, I think at this point, the last one is we do have the ability to do unary signed operators, pluses and minuses. These are a little tricky because these turn vectors. So these can be tricky because their actual impact on your bit vector can be confusing. So you have to use these with some caution and care because it may turn it into a 2's complement. And then multiplying and modulus and powers, these things are only, you can only use these on integer types. You can't use them on registers or wires. Okay. So the other thing to keep in mind is that we have order of precedence here. And the precedence is upside down, which is why it's always smart. It's always smart to apply. Use parentheses when you want to be clear. And if you don't use parentheses, then you have to have memorized this order of precedence. 6 is highest, next is 5, next is 4, next is 3, next is 2, next is 1. So you have to be careful. All right, let me give a minute for questions, and then we will pick up on Wednesday.
Professor,
yeah. Go ahead, John.
I think there operator with double curly braces is like replication or something like that.
Hmm. There, by no means is this all the operators in Verilog.
Okay.
There are a bunch of other operators, and some of them I just have not bothered to learn because I never use them. That would be one. If that's true, it could possibly be. I would not claim to know for sure. I've there are several though that are not included in here.
Okay. Okay.
And that may be one of them. So yeah, you can look that up.
Okay. Sounds good. Thank you, Professor.
Yeah, there are a number of really bizarre operators in Verilog, and they are not included in this chart. And we probably won't encounter them in this course. I mean, believe me, things like there's all sorts of we'll go over most of the stuff and we'll mention it in passing, but there are a bunch of commands in Verilog that are just really difficult to understand. So and we won't use them in this course. All right, anybody else? All right, very good. So this will be next week we'll have a shortened week, and Friday will be another somewhat complicated day for me. But other than that, then we hopefully will meet in person and everything will be cool. All right, we will see you then. You guys have a safe weekend. Do not drink and drive or do anything too crazy, and have a good time. And we will hopefully see you all safe back next week on Wednesday. And we will have lab though. So let me just say this. So the people who have lab on Monday, I know it's always a bit of a problem. We'll probably still try and get the lab done because it's real simple. So you can come in Wednesday if you want, or Tuesday at 11:30, or you can just do it at home. But remember, all the labs you have grace. You have grace until almost the end of the course to turn them in. So you can always just do 2 labs the following week. But I would like to keep moving and do the lab schedule for next week, even though we don't have a lab on Monday. All right, we'll see you later.